Okay, so we'll pick up where we left off and just kind of work through some examples. I'll introduce the idea of proportions today and briefly introduce the idea of confidence intervals, which we'll be primarily working on next week. So I think where we left off, if I recall, was thinking about, okay, now that we have this distribution that we know is normally distributed. So we're looking at the sample means. Oh, if I can get my mouse show up, there we go. They're normally distributed around whatever the mean was from the data you sampled from, and the variance of that distribution of our sample means is the original variance we sampled from divided by my sample size. So I can convert any value for that sample mean into a z-score, right? All I do is subtract the mean, which is right here, and then in the denominator we're dividing by the standard deviation, right? So if we're trying to kind of just remember what we were doing, kind of a brief review here, just to kind of give a little bit better context. We'll wait for this dot cam to catch up with us here. All right. So when we're calculating a z-score, we subtracted the mean and divided by the standard deviation. So we want to turn this sample mean into a z-score. What we're going to do is subtract the mean of my sample means and divide by the standard deviation of my sample means. Well, we know that the mean of my sample means is always just the mean of whatever the data I sampled from was. Let me see. This will auto. It's still a little fuzzy. Let's try this again. A little bit better. And I also know the standard deviation. I can write this a couple different ways. It's the square root of the original variance over my sample size, or the way I had it on the slide, another way of writing that looks something like this. Right? But all we're really doing is plugging those values in. So I will substitute this because I know what that is. And now that I know what my standard deviation is, I could plug that into my denominator as well. So it's really the same setup as what we were doing before. It's just now to calculate the standard deviation of my sample means, I have a little bit more work to do. Okay? And I'll show you kind of multiple ways of approaching this, kind of using this format of the formula or using this one. Okay? And I'll leave this up here if we're still kind of writing this down. So once we get the z-score, all the steps were the same thing we were doing before, right? We're looking for an area in the table. We look up the z-score. We can find the area to the left of that. And then maybe we have a little bit more work to do. So let's say we have this problem where we want to know what's the probability that if I take a sample of size, 100 from this variable, and then calculate the sample mean, what's the probability that sample mean? Hold on. I'll switch this over for you. That would help. Waiting on the screen in class. There we go. So we're going to be sampling from this variable, sample size 100, and now when we calculate our sample mean, what's the probability it's in between 10 and 15? Okay. So we're going to end up using this eventually, but we can think about this in some other ways. So we have this original variable, x. We know that it's distributed. I think we weren't told it's normally distributed. The mean is 5. And the variance, I believe, is 2,500. Right? So with that information, what we know is going to be true about our sample means, if we take samples of size 100, well, the central limit theorem is met. That's definitely greater than 30. So my sample means will be normally distributed around whatever that population mean was. Right? So it's going to have the exact same mean as the data we sampled from. However, we think about the variance here. The variance is going to be the original variance over my sample size, which my original variance is 2,500, sample size is 100, so I get a variance of 25. Another way of thinking about that is if I wanted the standard deviation, well, that's just the square root of the variance, or square root of 25, which is 5. The next part of the question asked, okay, what's the probability then I see a sample mean? Now that I know more about that distribution, what that looks like, what's the probability I see the sample mean be between 10 and 15? Okay. Well, right away, I know that this probability has to be less than a certain value. If I think about the mean, the area to the right, well, and to the left, really, of the mean should be 0.5. I want an area that is smaller than that, right? So right away, I know it has to be less than 0.5. From here, right, once I have this distribution of my sample means, well, it's a normal distribution, but it's not standard normal distributed, so I can't use that table yet. So what I'm going to do is turn these two values into z-scores. Right? Once I have some z-scores, I can work to find this area in between the two. Right? So how do I get my z-scores? Well, if I use this equation, right, all I have to do is plug in that value of 10 I was interested in. The mean was 5. And I could plug everything in here, right? This would be what? Square root of 2,500 divided by this, sorry. Yeah, so the original variance is 2,500. So the square root of 2,500 divided by the square root of 100. I can just plug those values in, get it entered into my calculator. Or I can remember, well, this entire denominator represents the standard deviation of my sample means. If I had already calculated the standard deviation of my sample means here, all I really have to do for this denominator is plug in that value of 5. Right? So that would just be plugging in that value of 5. Or I could write this out. It's going to be square root of 2,500, because that would give me the standard deviation, divided by the square root of my sample size. I can do it either way. So once I do that, I should get a z-score of 1. So if I enter this into my calculator, I should get a z-score of 1. But why? Well, let's think about it. Once we know we're looking at normal distribution, the z-scores tell us how many standard deviations away this value is from the mean. Right? So if the mean is 5, and I'm looking at 10, and my standard deviation is 5, well, I'm 5 away from the mean. That's 1 standard deviation. Sure enough, I end up with a z-score of 1. If I look at 15, I go through, plug everything in again, except for now instead of 10 here, the cutoff value I'm interested in is 15. Okay, so I look at this, I could plug all those numbers in and enter it into my calculator, or I could say, well, it's 10 away from 5. How many standard deviations would 10 be then? Well, if the standard deviation is 5, it's going to be 2 standard deviations above. Now, like I said, I can plug all those values into those formulas, and I'll get that z-score of 2. But this one was easy enough. The numbers were nice enough to where we could find that. Oh, I'm forgetting this isn't working. So let me leave this up here. Go back here for a second. So I've got this z-score of 1 and 2. So I can look that up in my table. So the z-score of 1, 1.00, 0.8413. Right? So when I'm thinking here, what I just found was this area to the left of 1, which is 0.8413. Then I could look up that z-score of 2. See if I can keep the column headings up here. So 2.00. The area to the left of that is 0.9772. So I use the table to find those areas to the left, and this is where I might have to do a little bit of work now, which is, if I know the area to the left of 1 is 0.84 and the area to the left of 2 is 0.97, what's in between them would just be, if I take kind of this red area and subtract that from the green area, where they overlap, that's what we kind of, I'm subtracting and cancel out, and I'm left with what I originally wanted. Right? So 0.9772 minus 0.8413 will give me that final answer I want, which is the area in between that z-score of 1 and that z-score of 2, which corresponds to the sample mean being between 10 and 5, or sorry, 10 and 5, 10 and 15. Okay. Any questions over that or clarification on anything? Okay. All right, so let's work through one more. So Here, if I plug everything in, this is going to be how I calculate those z-scores. We then talked about, okay, I'll look up the area to the left of each one of those z-scores, find those two areas. We can think about this as, if I took this bricked area and subtracted it from the blue, where they overlap is what will be canceled out, and I'm left with what I originally wanted, okay? And sure enough, it holds. We said at the very beginning it should be something less than 0.5, and sure enough, it is, right? So we just didn't make any egregious errors here. So what if I had a slightly different example? So we go back to that birth weight data, and let's say I sample, 81 different infants, and I know that the original kind of gestation weeks variable, because I had the population data, was 39 mean and a variance of 9, right? So if I look at these 81 infants, and then I take a sample mean from those 81, what's the probability it's going to be above 39.5? So how would we set this one up? If I can get this sheet off, there we go. So you always kind of can start out. You don't need to, but it kind of helps maybe to think about, I have this original variable x. It's the length of the pregnancy. It's got a mean of 39, and a variance, I believe, was 9. So what I know about my sample means, the distribution will be normally distributed because I had 81 was my sample size. I didn't draw this perfectly. Actually, this should be exactly kind of the middle. I'm not the perfect at drawing these. But I know that the mean of my sample means will be whatever the mean of the original data I sampled from was. The question then asked me, what's the probability I see a sample mean of 39.5 or greater? Okay. So I'll show you how you could work through this one. I'll show you two different ways. So here's the first way. Right? Well, either way, I need to turn that value of 39.5 into a z-score. Okay? So I need to turn this into a z-score. First of all, what should be true about the sign of this z-score? Well, if I'm looking at a value that's above the mean, it's going to be a certain number of standard deviations above the mean, so it should be positive, right? Not only that, right away I can say, well, here's the mean. I know the area to the left and the right of the mean is 0.5, so I want something smaller than that, right? So right away I know it has to be positive and it has to be less than 0.5. Sorry, I know the z-score has to be positive and the probability has to be less than 0.5. Got ahead of myself there. So I could have went about it this way, right? I've got my, try to slide this up, my z-score equation, which is, looks like this. And we could look at it a couple different ways. I'll write it the easiest way. So there we go. Well, I know that the cutoff value I'm interested in is 39.5. The mean was 39. The variance of the original data we sampled from was 9, and the sample size was 81. Okay? So, I believe if I do this, let me see, this would be 0.5, 1/3, or wait, 1/9, so 1/3. I think this should be 1.5. Okay? If I'm doing the math in my head correct here. Okay? And I wanted, remember, originally, I wanted the area to the right of that. So, I could look this value up in my table, right? I could look 1.5 up in the table. If I do that, let's see, I'll come back here in a second. Just going to pull up the table real quick so you can see me using that so we get more practice. So the z-score of 1.5, so 1.5, 1.50, right, would be the second decimal. So I go over 0.9332. Okay. So the area to the left of that z-score is 0.9332. That's not what I wanted. I wanted the area to the right. Well, the area under the curve is 1, so I just have to subtract that from 1. Okay. So that's one way you could work through this. Right? and it just kind of depends how your brain works, but there's another way that to me, it at least lets me think a little bit more intuitively about it. Because if I'm using this, I'm just like plugging values into this formula, and it's a little bit easy to get lost in that. So I'll use kind of I guess I'll use the green marker to show you that we could do it instead. So what if instead, when I got to this point, and I'm thinking about, actually we'll go up here, we got a little bit of room left. And I'm thinking, okay, 39.5, right? Well, originally I look at that, I'm like, well, that's not very far away from the mean, right? So it's gonna have a relatively low z-score, right? It's not very far. The problem is, even though I'm 0.5 away, right? If my standard deviation was 0.1, then being 0.5 away is 5 standard deviations away, right? So even though the gap in between the mean and the value that I'm interested in for this sample mean, even though that distance isn't very far, if my standard deviation is small, that's going to be a lot of standard deviations away. Right? So maybe I go ahead first and think about, okay, what is the standard deviation of my sample means here? Well, that's going to be the square root of the original variance divided by my sample size, right? Or if I think about if I'm writing this out generally, the original variance over my sample size. So I'm just plugging those values in there. So if I do this, I'll go ahead and calculate this, and I get 1/3. Right? So 1/3 is 0.333. Repeated. I'm 0.5 away, so I'm more than 1 standard deviation away. So even though the gap in between these two values isn't very large, it's more than 1 standard deviation away, right? In fact, when we calculate it, it's 1.5 standard deviations away. Right? Now, that doesn't necessarily, that kind of helps me think about it a little bit better, but it also allows me, instead of using this form of the formula, I can remember really where does this come from. It's because anytime I want a z-score, I subtract the mean of the statistic I'm interested in, and I divide by the standard deviation of the statistic I'm interested in. Well, what's the mean of the standard deviation in the statistic I'm interested in? So 39, so 39.5 minus 39 divided by the standard deviation, which if I've already calculated it ahead of time, I can just plug that into my denominator. Right? So here, it was kind of like I did an intermediate step. I first calculated the standard deviation, then I plugged it in. But here it's already like, notice this, right, is kind of plugged into the denominator, right? So it's kind of all in one step. So this was representing the standard deviation of my sample means. So kind of two ways of doing it. I guess this way it allows you to kind of see what the standard deviation is on your sample mean distribution. And just think about, okay, I know that this is pretty close to the mean, but if my standard deviation is really low, that doesn't mean anything. If my standard deviation was 0.1, this would be 5 standard deviations away. And that's the whole point of creating these z-scores. So I had someone yesterday in a section ask me about this, and hopefully I can get the analogy I use correct. But if we think about something like height, right? So maybe the average height is something like, 5'8", and if the standard deviation on height is 3 inches, right? Well, even if I see something that's, someone that, let's say, 6 foot, right? That's 4 inches away, right? It's not very far, but if the standard deviation is only 3, that's more than a standard deviation away from the mean. So there, even though we had a value pretty close to the mean, right? It's only 4 away. Well, that's more than 1 standard deviation. Whereas if I had a variable like income, maybe the average income is 50,000, and I see a sample mean of, 52,000. Right, so it's 2,000 away, right? With the height one, I was only 4 away, but now I'm 2,000 away. But the standard deviation on income, the sample means for income, might be something like 10,000. So even though I'm 2,000 away, I'm a fifth of a standard deviation away. So once we turn these into z-scores, all the units, kind of everything is, I don't want to say they're canceled, but essentially we're unitless, right? We're kind of thinking about things now in the same context. How many standard deviations away am I? And just because I'm 0.5 away or I'm 2,000 away, that means nothing if I don't know what the standard deviation is. Because being 2,000 away could be way less than a standard deviation away from the mean, depending on what variable I'm looking at. So that's why we're getting it down to kind of transforming everything to that same standard normal distribution. All right. So that one. So kind of what we worked through here, I have a slide that kind of mimics everything I did by hand. Shouldn't be too tough, shouldn't be too bad. Okay. So we're gonna look at something a little bit different here. Oh, I got a question coming in. If the second way is harder, you can do it whichever way makes most sense to you, right? It doesn't really matter if you calculate that standard deviation first. Let me see, where was that? Right, it doesn't matter if you kind of do it the way I did it in green, or you do, or is it? There we go. The way I did it in the green marker, or if you just kind of plug everything in there, that's fine. Right? Both ways will get the same answer, and both ways are appropriate. It's just sometimes it's a little bit easier for people to think about it if they calculate that standard deviation ahead of time. But it's really kind of personal preference. All right, so the next thing, we're going to go back and kind of relate this to some stuff we talked about before the first exam. So when we were looking at the binomial distribution, we had this equation for the mean and this equation for the variance. So this was giving me the number of successes that we expected, out of 150 or out of 200 or out of 30. So whatever the expected number of successes was, that was our equation for the mean. So we can think about this. Oh, we got another question. Oh, no. Okay. So we can think about this and ignore this as our old work, but I just want to kill as few trees as possible here. So we've got the average number of successes, right? So if I wanted the proportion, like let's say, I'm flipping a coin 100 times, it's a fair coin, right? So the expected value is kind of 50. That's the mean. But this is the expected number of heads I see. If I want the proportion of heads that I'll see, well, I would actually just take this and divide it by my sample size, right? Divide by 100, and kind of my mean proportion would be 0.5, right? So just dividing by n. Same thing with the variance. Before, when we had the number of successes, this is what it was. But if I want the proportion of times that it's a success, I divide by the total number of observations. And so my variance and the mean of my proportion is going to just simply be p, and then p times 1 minus p. And so that's where this comes, maybe that's where this comes from. There we go. So if I'm looking at proportions where, let's say I've got a sample size of 100, and I asked people if they were in favor of some new policy, I could find the proportion of people who were in favor of that policy. Maybe 40 people said yes, they were. So 40 out of 100, 0.4. Right? So this sample proportion has to be between what two values? Well, the lowest it could be is 0 out of anything, so 0. And then the most of that proportion could be is if all the options, like I say, everybody was in favor of this policy, 100 out of 100 or 1. Right? So proportion is going to be somewhere between 0 and 1. And my distribution of this proportion will be centered around whatever the true population proportion is. And the variance will be, well, what would the original variance have been? I had kind of showed you that here, divided by my sample size, just like we did for the sample means. So I'll kind of draw these two things back to back and then remind me to show you something in Excel. So just to kind of relate these two things, with our sample means, they were normally distributed if we had a sample size over 30. The mean of my sample means was that population mean, and the variance of my sample means was the original variance of the data I sampled from over my sample size. If I'm thinking about the distribution of my sample proportions, as long as I have a sample size over 30, they'll be normally distributed, and the mean of my sample proportions, well, it won't be centered around the true mean because I'm now looking at proportion. It's going to be centered around that true population proportion. And then the variance of my sample proportions, well, if we look back here, I said the variance on the original kind of variable would just be p times 1 minus p. So here's like the original variance divided by my sample size. So it's just here that the way that we calculate the variance, we have a slightly different way if we know that it's a proportion example. Now, we're thinking about proportions, one that we actually already looked at last class when I talked about that maternal smoking variable. It was 1 or 0, right? So I was basically just saying, okay, what proportion of mothers smoke, count up the number of mothers who smoke, divided by the total number of observations. So when we're thinking about how am I calculating this sample proportion, well, it's really going to be kind of the number of successes you see out of the total number of observations. So the reason why all this holds for sample proportions as well, because sample proportions are really just a unique type of sample mean. So let me show you in Excel what this would look like. So if we had a binomial, oh, I already had some stuff in here. So if I started a new worksheet and then said, let's say I had a small data set with whether or not someone had blue eyes or whether they didn't, all right? So just a 1 or a 0. Well, if I find the mean, right, using the average function in Excel of this variable, what the mean will do is count up, right, add up all these values and then divide by the total number of observations. Well, the thing is, when I'm adding up all these values, the only thing that really does anything is if someone has blue eyes, because otherwise I'm just adding zeros. So the numerator of my mean will really just be counting the number of people with blue eyes and then dividing it by the total number of observations. Or what I kind of like what I just said, which was the number of successes, here the number of people with blue eyes, divided by the total number of observations. So finding the mean of a 1-0 variable really just gives you kind of your sample proportion, okay? Because all that's going to do is count up the number of ones and then divide by the total number of observations. So notice here I can do this on my hand and prove it to you, right? So 1, 2, 3, 4, 5, 6, 7. 7 people with blue eyes out of the 13 observations. So hopefully, if I'm not lying to you, 7 out of 13 should be exactly what finding the mean did for me, okay? So the mean of a 1-0 variable is really just giving you the sample proportion. So that's why everything applies from what we were talking about before, because it's really just a sample mean that's, you know, a little bit different, right? Because the responses can only be of 2 types, 1 or 0. What else did I want to show you here? You could also think about, let me do standard deviation. Or actually, let's do the variance. So if we wanted to find the variance here, hopefully that is, might not work because my data set's too small, but, all right. If I find the variance, oops, of this data set, if what I told you was true, it should just be P, right, the population proportion times 1 minus P. And sure enough, it is. Right? So just kind of proving to ourselves that these things are true with data, I think is always useful. All right, so you can kind of imagine, if I now know the mean of my sample proportions and the variance of my sample proportions, well, now my z-score, well, I'm looking at a different statistic. So instead of, let me see where I had the old one written down if I can find it. I might just rewrite it again. Oh, here we go. I'll kind of show you how we built this. So earlier when we were talking about, you know, when I had my just original variable, this is how I found a z-score, sample mean. Well, now I need to subtract the mean and the standard deviation of the statistic I'm interested in. And then we kind of talked about that. Well, now if I want the z-score for my sample proportions, it's the exact same format. I take the statistic I'm interested in, I subtract the mean of that statistic I'm interested in, and I divide by the standard deviation of that statistic I'm interested in. Now, here, I know the mean of my sample proportions is just whatever that population proportion is. And the standard deviation will be the square root of P times 1 minus P divided by my sample size. Right? So all the, these z-scores are starting out with the same format. It's just usually finding the standard deviation. We can plug in kind of another equation in, into this formula. Or just like we did before, I could actually break this down, calculate an intermediate step, which is first calculate the standard deviation and then kind of plug it in. So once again, we'll have kind of two ways we could approach a lot of these sample proportion problems. All right, there we go. So that's how we get this equation for the z-score. Any questions at this point? I hate not checking, forgetting to check the chat. Okay. So I already mentioned that really it's just it's a sample, a proportion. A sample proportion is a sample mean, just kind of a unique circumstance. So as long as we get over 30, we can apply that central limit theorem and kind of work out problems in a similar manner as to what we did with sample means. So let's say we want to know what's the probability of getting 55 or more heads in 100 coin flips. Okay. So 55 or more heads in 100 coin flips. So start out very similar to how we did the sample mean problems. I know that my original data, like if I could flip a coin an infinite number of times, the different values I would see would kind of be centered around that true population proportion. And I could think about the variance would be just p times 1 minus p. So what that tells me is that for my sample proportions, as long as I get a sample size of 30, they'll be normally distributed. They'll be still centered around that population proportion, which for a kind of coin example, a fair coin example, that would be 0.5. I also could calculate my intermediate step. Let's say I wanted to find the standard deviation, not of my sample means, standard deviation of my sample proportions. Well, that's just the square root of p times 1 minus p over my sample size. Now, one thing I did here that's not technically correct, I just draw it because it's the easiest one for me to draw. But for the original variable that we were sampling from, it's not technically normally distributed, but it doesn't matter, right? As long as that central limit theorem is met, we have a sample size of 30, I know that my sample proportions will be normally distributed. So, if I really wanted to draw this more accurate, I think it looks something, it's going to be a binomial, so it's going to be a little bit kind of skewed. Although because we have 0.5, actually, I think I probably was right here. It will look normal, but it doesn't matter what it starts out as. All we need to know is the variance and the mean, and then we can determine what the distribution of our sample proportions look like. So at this point, I think the question asks, well, what's the probability I get 55 out of 100 heads or more? So why did I know to draw this out here? Well, that sample proportion value I'm interested in would be 55 out of 100 or 0.55. Okay. Now, I don't know how many standard deviations away that is yet, right? I could figure it out, right? I could do, square root of 0.5 times 0.5 divided by 100. So what, 0.25? Yeah, it's going to be pretty small. We'll end up seeing what this works out to be here in just a second. But the next step that I need to do is turn this normal distribution into a standard normal distribution. So how am I going to do that? Well, I have the equation for my z-score right here. So it's just a matter of starting to plug things in, right? This is going to be 0.55. That was that cutoff value I was interested in. Population proportion was 0.5, 0.5, 0.5, 100. I've now got everything plugged in to be able to enter this into my calculator. Okay. So if I do that, I think I get a nice, easy number to deal with, but let's see, because I can't do that math in my head quite right. So I get that entered in to my calculator and I get a z-score of 1. So I'm 1 standard deviation away. So what I'm thinking about now is that I'm 1 standard deviation away. Get on my laptop bag here. So I want the area to the right. I can go to the table, look this area up, we looked it up earlier, actually. We had a z-score of 1 earlier. So I won't kind of open the table up here and interrupt this because we've already done it. Once I look up the z-score of 1 once, it's always going to tell me the same value. So if I go back, sure enough, we looked it up and it was 0.8413. So I want the area to the right, so I have that kind of fifth and final step, which is sometimes I have to transform these probabilities. Here, all I have to do is subtract it from 1, so 0.1587 ends up being what I get. Any questions on that? You know, once we get to the z-score, the steps are identical, right? The only real difference is when we're calculating that z-score, we now have a slightly different, go back here, slightly different equation than what we were using with sample means, okay? Any questions on that one before we keep moving? Do one more sample proportion example, and then I want to introduce confidence intervals today. So what if we had a similar example, but I want to know what's the probability of getting 66 or more flips to show up heads, right? So it's the exact same setup, right? So we'll just kind of skip a step here and start to think about, okay, how are my sample proportions going to be distributed? Well, I've got a sample size of 144, so I know they'll be normally distributed, and they should be centered around that population proportion of 0.5. What's the variance of my sample proportion is going to be? It's going to be p times 1 minus p divided by n. Right? Or here I can plug this in, right? 0.5 times 0.5 divided by 144 now. Right? So the question asks, what's the probability I see 66 over 144 or more? Right? So if I do 66 over 144, oh, I have to pull up Excel. I can't do that one. It's probably something really easy. Oh, hold on. All right, there we go. Now I can hit escape. So it's what, 66 out of 144. So about 0.46. I'll just use 0.46 to kind of abbreviate that. So 0.46, and I want the probability of seeing that or anything more. So right away, I know this probability has to be what? Well, if I think about the mean, the area to the left and the right of the mean is 0.5. So I want an area larger than that. So right away, I know my probability has to be larger than 0.5. Right? Once we go back to the slides in a second, we'll think about that. We probably can rule out quite a few of those, or at least a couple of those answers. So the next step is I need to turn this normal distribution into a standard normal distribution and convert this value of 0.46 into a z-score. So I've got what? Kind of write this out. So here is the equation we had for our z-score. The sample proportion we're interested in is 0.46. Population proportion is 0.5. Sample size is 144. Okay. So if I enter this into my calculator, oh, I have a feeling we get a z-score of -1, but I don't want to say that if it's not right. Yep, sure enough, we get a z-score of -1, right? So I just found a z-score of -1, and I want the area to the right of it. Now, if I look this value up in the table, here's where I want to highlight something. Well, before, when I looked up a z-score of 1, the area to the right of it was 0.1587. Well, if this is a symmetric distribution and it's centered around, right, their standard normal distribution is centered around 0, then the area to the left of -1 should be the same as the area to the right of +1. So this area should be 0.1587. I then wanted the area to the right So I'll subtract that from 1. And now I'm done, right? Now, we had that previous work done, and I wanted to make that connection that, you know, if I'm thinking about the same z-score, but one's positive, one's negative, the area to the left of that negative 1 z-score is the same as the area to the right of that positive 1 z-score, because this is a symmetric distribution. Now, if I wanted to go ahead and look up that z-score of -1, I very well could have done that. So remember that first column is 0.0, so -1.00, 0.1587. Sure enough, that's exactly what I was saying earlier. Okay. Any questions on that one before we kind of keep moving here? We're okay with that? Yeah, so once we get to the z-score, I mean, really everything kind of looks the same as what we were doing with sample mean problems. So I want to introduce the next idea. So we kind of start out next week having a little bit of an idea about what we're doing with confidence intervals. So 99% of the time, we don't know where the population mean is, right? We don't have population data. You know, I'm setting up all these examples like we know the population mean, we know the population proportion, but you know, the majority of the time, we're only going to have one sample mean or one sample proportion. So what we want to do is try to use these sample means or these sample proportions to predict where that true population mean is. Kind of the idea here is, you know, if I know that my sample means are normally distributed around the population mean, well then if I see a sample mean of, I don't know, 50, it's very unlikely the true population mean is, I don't know, 50,000, right? I mean, so I know that my sample mean is a pretty, you know, could be a good indicator of around where that population mean is. So what we want to try to do is have predictions that are unbiased. So we talked about this, you know, at length this week about eliminating bias from our samples. But we also want a small variance, right? So we want to try to decrease the variation that exists in our sample statistics. What's one way we can do that? Well, I've already got a lot of this. Where's the one that I really wanted? Here we go. So notice in each, you know, anytime we're calculating these standard deviations, right? Or you kind of think about the variance, we're dividing by n. So if that denominator gets larger, that would drive down our standard deviation, right? If n starts to get really large, we can really reduce the variance or the standard deviation for our sample statistics. So that's going to be the one thing that we try to control, and we can do that by taking a, you know, get a smaller variance. We can take higher sample sizes. That's the main way we can do that. Can't really change anything about the original variance of the data. So what we're going to do is we're going to use this sample mean or sample proportion and then build a range of values that we can say with certain levels of confidence the true mean or the true proportion, population proportion, is somewhere in this range of values. So what we'll do is we'll take a sample, calculate that sample mean. You know, maybe we do this for birth weights in a hospital. Once I have that sample mean, what I'll do is, I'm skipping ahead a little bit here, I'm going to build a lower bound and an upper bound around that sample mean. So I'm going to go a certain distance to the left and to the right of that sample mean I saw. I'm going to create my lower and my upper bound, and then I'm going to say things like, with 90% confidence, I can say the true population mean is somewhere in this range of values. Right? So in practice, what we're going to do is we're going to take our sample mean, we're going to add something to it and subtract something from it to build our lower and kind of our, not UB, yeah, upper bound, my bad, upper bound. Right? You know, so if I see like a sample mean of 10, maybe my lower bound is 8 and my upper bound is 12. And then I say, based off of the sample mean I saw, I can tell you with 90% confidence that the true population mean is somewhere in this range of values. Okay? It's kind of the setup for what we're going to be doing. But what are different levels of confidence? Like, how do I determine what this value for W should be? I introduced the idea today, and I'm sure we'll review it a little bit on Monday, but I can use that normal distribution because I know that sample means will be normally distributed. There's a couple things that I can with certainty say. So let's say I want to say something with 95% confidence. Well, if I go back to my original kind of normal distribution, if I go 1.96 standard deviations below the mean, right? I know the probability I see something 1.96 standard deviations below the mean is always going to be 0.025. Because if I'm 1.96 standard deviations below the mean, that also means I have a z-score of negative 1.96, which if I look that up in the table, negative 1.96, 0.025 is always the area to the left of that. Okay? So if the area to the left of negative 1.96 was 0.025, then if I have a z-score of 1.96 or go 1.96 standard deviations above the mean, the area to the right of that is also 0.025. So I can say that if I go 1.96 standard deviations below and above the mean, the probability that my sample mean is somewhere within 1.96 standard deviations above and below the mean, there's a 95% chance that it's within that blue range, right? There's only a 5% chance that it's more than 1.96 standard deviations away from the mean, right? Above or below. Like we know that's true. That just comes straight from our understanding of a normal and a standard normal distribution. So what ends up being true is that if I start to then take my sample, and we'll use sample mean in this case, if I see a sample mean that's right here, and I then build my confidence interval around that sample mean by going 1.96 standard deviations above and below my sample mean, well, I'm guaranteed that that confidence interval includes the population mean, because if it's not more than 1.96 standard deviations below, then when I add 1.96 standard deviations to that sample mean, it'll go back past the population mean. And then if I had another mean that was somewhere over here, well now, if it's less than 1.96 standard deviations away, when I when I go back 1.96 standard deviations below it, it'll kind of extend past that population mean. So any sample mean in this blue area, when we build our confidence interval around it, it would include that true population mean. Now, if we get a sample mean that's more than 1.96 standard deviations away, it's not very likely. There's a 5% chance of that occurring. But if we did end up with just this one sample mean and we built our confidence interval, it wouldn't include, right, that true population mean. So when we build our confidence intervals around our sample, for every sample mean in this blue area, we'd be right. Well, there's a 95% chance we see a sample mean in this blue area. So my confidence interval will include the population mean 95% of the time. Now, the other 5% of the time, where I see a sample mean that's more than 1.96 standard deviations away from that true population mean, my confidence interval will be wrong, right? So when I build my confidence interval around the sample mean, that's why I'm saying with 95% confidence, I can tell you this. Because 95% of the time, the confidence interval will include the population mean, and 5% of the time, it'll be wrong. So that's kind of the general idea of what we're doing. I'll probably revisit this. I think I'm going to draw it out by hand and do things a little bit different and give you a slightly better, I think, approach to it. But I just want to set this up today to start to think about what we're going to be doing with these confidence intervals. So right now, kind of the main thing you should be working on is that connect assignment. So we'll be able to get pretty far through it. I think some of the last questions on it might be some confidence interval stuff. So next week, you might have a few of the problems that you have to kind of finish up once we cover the confidence interval chapter. But other than that, should be able to get most of the way through it. I won't put an online quiz up today, kind of give you the weekend off from that. And unless there's other questions for me. Questions? All right. I will see you guys on Monday.